I have spent the last 50 years studying how nature builds designs with maximum structural integrity while at the same time using a minimum investment of material, space, or effort. These videos will focus on the practical applications of the synergetic interconnectedness of basic structure. Design found in nature teaches us how to do more by using less. You can use a portion of a rhombic dodecahedron to make a dish draining structure that drains into the sink without interfering with dishwashing. You can achieve maximum use of space while using less material by adopting natural modular building techniques. Modular building design needs a major reboot that is based on whole systems thinking, finding the interconnectedness of essential parts of structure. I began my personal exploration of natural design with the work of Buckminster Fuller's Synergetic Geometry 1 and 2. This image from his work was my jumping off point where I understood you can find the fundamental interconnectedness of essential parts by thinking of structures like nesting dolls, one fitting inside the other in succession. My first discovery was the cubes that exist inside the geometrical systems of basic structure. People generally think of space in cubes, but cubes have a secret life that reveal the modular building patterns of natural design. A simple cube has a significant structural memory that defines the communication networks that link its center to the outside limits of its growth. The cube remembers three landmarks: the relative size field, the equator, and the axis of spin, which aligns any subsequent structure. Double the size of a cube and you increase its volume 8 times. There is a 1:8 ratio. This defines the first all-space filling state where cubes, when stacked together, have no gaps between them. Thus the cube is in the sphere family. Connect the midpoints of the edges of the cube and you construct a 14-sided VE inside it. The 8 outside corners can be defined by 2 interconnected tetras spinning in opposite directions called a duotet. 3 couplers interconnect the midpoints of the cube and define the structural integrity inside the interior of the VE. The cube begins by defining the synergy, the interconnectedness of the VE tetra and coupler. If you take the volume of a cube and turn it inside out, you form a 12-sided rhombic dodecahedron, R dodeca. The R dodeca is the outside containment field of any sphere. Thus the cube remembers how spheres closest pack. This connects the cube to all the essential parts that define simple structure. Let's go back to the cubes inside the synergetic 10. Our simplified big picture of basic structure. The sphere family has 6 systems in this group, and the bubble family has 4. We will use Buckminster Fuller's relative volume system based on 1 tetravolume, TV. This is the volume inside an equal-sided tetrahedron. I choose the 6BB equals 12 centimeter edge tetra as 1 tetravolume. The VE then has 20 TVs. The R dodeca has 6, the cube has 3, and the octa has 4. If you will notice, even though the 2 structures look so different, the coupler and the tetra share the same 1 TV volume. They have a deep interconnectedness. The volumes inside the bubble family are not symmetrically connected to the sphere family. The T module defines the volume of the triacontahedron, and by slicing off the top of this module, defines the rest of the systems in the bubble family. The sphere family's volumes are defined by the A and B modules. These 3 volume modules are the most effective minimum essential parts. You cannot divide the volumes of fundamental structures into smaller units than these. They are the quantum volumes. I will go into detail of how to mass produce these units in subsequent videos. What is important to remember right now is that these systems define volume as synergetic, meaning all volumes are interconnected in some way. When I built the physical models of the cubes inside the sphere family, I discovered a series of structural numerical constants that fit a pattern. All of this was discovered by trial and error and a calculator using only addition, subtraction, multiplication, and division. Look at the square root of 2 3bb cube that fits inside the R dodeca. With the A and B modules, we know its volume is 3 TV. Divide that volume by 27 and you get the 1/9 TV, which is the volume of the cube inside the 6bb tetra with the edge of square root of 2bb. All of the other cubes in the sphere family are multiples of this volume and edge length. We know if you double the size of a structure, you increase its volume by 8, a 1:8 ratio. If you triple the size, we now know you increase its volume 27 times, a 1:27 ratio. This is always true. The cube inside the 6bbVE has an edge of a square root of 2 4bb and a volume of 64/9 TV. The edges of this cube are divided by 4, so there are 4 by 4 by 4 equals 64 small cubes that add up to 64. 64 divided by 9 equals 7.1111 tetravolumes. The cube inside the octa is the square root of 2 2bb and has a volume of 8/9 TV. The tetras cube inside has an edge of the square root of 2bb and the volume of 1/9 TV. These numerical and structural constants use the same patterns with the other sphere family structures. The cube that is the outside containment field around the 6bbVE has an edge of the square root of 2 6bb and a volume of 24 TVs. The cube inside the R dodeca is a square root of 2 3bb edge and 3 TVs, and the cube inside the coupler edge is the square root of 2 1.5bb, and its volume is 6/9 or 2/3 TV. Here you can see the cubes inside the sphere family. This 1/9 tetravolume is the modular unit of measure. There was one more practical building constant I found in my trial and error calculations. I saw I needed to convert all the bb numbers to 6bb to know what was the underlying numerical constant. The VE's cube's edge was the square root of 2 4bb. 4bb is 2/3 of 6bb. 2/3 in decimal form is 0.66666, which is less than 1, so we multiply to find our number. The square root of 2 times 2/3 equals the square root of 8/9, or in decimals, the square root of 0.88888. Take the square root of these numbers and you get the number 0.94280 ... Once I understood the pattern, it became simple. The octa's cube was 1/2 the edge of the cube inside the VE, so I needed to multiply the square root of 2 by 1/3, which equals the square root of 2/9, or the square root of 0.2222 ... The square root of these numbers is 0.471405 ... Finally, the tetras cube is 1/2 the size of the octas, so I need to multiply the square root of 2 by 1/6, which equals the square root of 1/18, or the square root of 0.0555 ... The square root of these numbers is 0.235702 ... This will become very practical when you want to try to find the cube that fits exactly inside the icosa. There is a structural constant that can build any icosa inside an octa or vice versa. To find the cube inside an icosa, convert the icosa to an octa and multiply the edge of the octa by the square root of 2/9, and you have the cube inside the icosa. In the next video, we will explore the cubes inside the bubble family. I have spent this much time on the ins and outs of the cubes fitting inside fundamental structures, because it was the first time I understood the practical value of the search for synergy among essential parts. I finally understood everything was symmetrically and exactly connected to everything else.